David is an expert in geophysical fluid dynamics, especially theory and numerical methods. Today, he's going to tell us about the late time behavior found in Viscid 2D or QG flow.
Thank you to the organizers for giving me this opportunity to talk here. It's actually probably everybody says this, my first in-person talk in several years, but it's a strange experience. So this is work that actually began at a KITP program with Brad Marston and Wanming Key back in 2014, and then developed into a study that was published in Journal of Fluid Mechanics a couple of years later, which is the first part of the talk. And then some more recent work is with Helen Burgess, who had been a Leverhulme Fellow in St Andrews for the last 4 years and now is a postdoc at Manchester in the UK. But she's been working on all kinds of aspects of geophysical turbulence in collaboration also with Richard Scott, that some people might know about. We've been studying things like the formation of jets on Jupiter and banded circulation patterns and such. I'm going to talk today about probably a more basic, more theoretical problem, which nonetheless requires some degree of computation or computational finesse in order to really describe what might take place. I'm not going to argue that the problem is, actually the pointer has disappeared. It used to be here. But this is it. Okay, it looked like another pen. Sorry. Okay. Pen in disguise. Pointer disguise. So the work really is. I'm not going to argue that this is particularly relevant to real geophysical flows, except that the question of looking at the evolution of a geophysical flow at ultra high Reynolds numbers is, of course, relevant. The actual atmosphere is computed in weather forecasting client models at very coarse resolutions compared to the ultimate viscous scale that matters. People come up with all kinds of so-called parameterizations and models of effects that we don't understand yet, and that's necessary for, say, running a climate or a weather forecasting model. So I'm not interested in those aspects. I'm not trying to sort of cheat the system by putting in fudge factors to control the numerics here. In fact, I'm going to use a particular type of method, which I'll describe only briefly, but later on this afternoon, I can go into some more detail for people who are interested on some of the methods that go behind the computations here. But this first part of the work with Wanming Key and Brad Marston, we actually used two different numerical methods to study this problem. And this is actually how it developed. When I was at KITP, I was looking at some results that Wanming was showing me is some work that they were doing in spherical flows. That was, I think, for her PhD thesis. And at that point, I thought that, well, there's some odd behavior. I'm very much against the use of hyperviscosity, although I have used that before in other contexts. But it's very easy to fool yourself in numerical simulations and believe that hyperviscosity is a benign effect. It's there to, especially in spectral models, it's a very simple addition where you only have to multiply by a total wave number to some power, and you can incorporate the diffusion, the hyperdiffusion, directly into your time stepping. It's extremely convenient, and as a result of that convenience, it's become widespread in use and largely forgotten in terms of its effect. But it was actually looking at Wanming's results originally that I noticed that they were contaminated by hyperviscosity. People tend to use hyperviscosity at too low a coefficient, which is numerically stable, but physically inaccurate. So we had to go back and revisit these calculations so that we could adjust for this effect of hyperviscosity. We try to reduce its minimum to a minimum level. So I'll describe first the mathematical problem, the setup that we're going to, in the first stage, looking at the simplest flow you can imagine, probably the simplest flow. So we're looking at an isotropic sphere, non-rotating. Okay, so geophysically probably irrelevant, but we're looking at just the reason for using a sphere is that a sphere is a bounded surface. Just like a doubly periodic box would be bounded, but doubly periodicity has other things that make it non-isotropic. So there you don't have as many conserved quantities in a doubly periodic domain than you have in a sphere. On a sphere, if it's inviscid, you have not only energy, but you have all three components of angular momentum, as well as a whole set of so-called Casimirs, which I'll come to in a bit, that have to do with conservation of vorticity, material conservation of vorticity. And that those conservation properties are built into one of the numerical methods that I'll describe. I'm not, again, saying that we have the perfect numerics. There isn't such a thing as perfect numerics unless you happen to have an algebraic problem that you can solve exactly. We're all making approximations, and the numerical methods are no different in that sense. It's just that they make different approximations. So we use two different numerical methods, so that both of which were so entirely different, to see if we could achieve similar results in the end. And that's basically the first thing, to look at the effect of two-dimensional. Sometimes in the field of geophysical fluid dynamics, it's miscalled or misnamed, named barotropic. So this is not anything to do with pressure. It's basically a statement that the flow is independent of depth, and that the surface, you think about a surface of fluid on a spherical body, that this surface has uniform depth. So it's a extreme limit of the shallow water equations, where you can't deform the free surface of the flow, and the fluid is forced to move tangent to the surface. It's actually been a nice geometry for a number of people to study, but in this context of looking at sort of more pure problems, by far and away, people have used doubly periodic geometry because it's just easier to write a spectral model. You can write it in a few tens of lines of code, pretty much, and you can run that in doubly periodic geometry. On a sphere, of course, things are more challenging. You have to think about the grid, which is no longer uniform. You have polar singularities that are only apparent singularities, not real singularities, but they have to do with coordinate singularities. That causes trouble for numerics. If you use expansions, you don't have the nice property of Fourier transforms, where you have a especially fast Fourier transform. You have to use the Rome transformations. So spheres are not nice in that sense. And so people have largely avoided looking at the surface of a sphere in more theoretical work. That's not to say that people do that in weather forecasting. Of course, we have to use spherical surfaces. In fact, the real surface we should be looking at is something oblate spheroidal, and people take into account these effects as well when they do weather forecasting, climate modeling. And for certain planets like Jupiter and Saturn, the oblateness of the planet actually has some significant role to play. Again, I'm not going to talk about that. I have some expertise in looking at deformed surfaces and flow on these surfaces, which is itself, I could give another talk on that. There's some fascinating results having to do with flow on surfaces that are deformed from spheres, so ellipsoids, and they have their own fascinating properties, and things that you think you know on a sphere actually can change dramatically when you deform the spherical surface. But again, I'm happy to answer questions about that, but that's not the main purpose today. The second half of the talk will be concerning what's called quasi-geostrophic flow. And for those who don't really understand where quasi-geostrophic flow comes from, this afternoon I'll give a little tutorial about where this model is derived from. The talk this afternoon is really about how we derive so-called reduced models in geophysical fluid dynamics. It's been a business that people that have been involved in historically for a very long time, going back to the famous experiment by Lewis Fry Richardson, who actually was the first director of the Met Office in the UK. And he had the idea, the famous experiment where before computers were available, he put everybody in rooms like here, but many more people, and they tried to forecast the weather, because they said, okay, we know the equations, the Navier-Stokes equations, we can put rotation in them, you can write them down. So he thought, well, all we have to do is just pass the information back and forth. So he set up like a finite difference scheme, and he had people passing information back and forth between people. So this is the famous experiment of Richardson. And its results were completely inaccurate. So his simulation of the weather blew up after a very short time, and they didn't understand why. So they thought, well, we have the equations, but we can't solve them. Well, that hasn't really changed in some ways. We still have problem-solving equations. Equations of fluid dynamics are particularly notoriously difficult. Throw in magnetic fields, as we discussed yesterday, it gets even worse. But the essential nonlinearity is this advective nonlinearity, also vortex stretching when you start looking at 3D flows. So anyway, I'll be talking about the so-called quasi-strophic system, and I'll explain where this comes from when I get there. And in particular, we'll be focusing on what's called a small deformation length. So just to give you a little bit of background before I go into it again, because I probably won't spend much time on the fundamental origin of the model in this talk, is that the deformation length has to do with the fact that in a quasi-strophic flow, there is a free surface variation, and it can occur over typical scales that are comparable to the deformation length. This length is a number that people often quote for, like the gas giants, like Jupiter, Saturn, Neptune. People have been doing simulations of their atmospheres using so-called shallow water models, which is what I call a parent model for the quasi-strophic model. Again, in my talk this afternoon, I'll talk about this idea of a parent and child model, if you like, how you derive these. But the shallow water model or the quasi-strophic model has this intrinsic length here, which controls typical scales of motion for small perturbations. So if you take a localized perturbation, that perturbation will fall off on a scale of like LD. So I think in plasma physics, this is a Debye length or something. I'm not a plasma physicist, so there's a similar length that appears in plasma physics. And in fact, the model itself is called the Charney-Hasegawa-Mima model. It's another name for this same flow model. And then I'll go into some conclusions and then discuss some ideas for future work, some things we're doing, and then ideas that could extend this work further. And I'm happy to have questions at any moment. So the mathematical problem is very simple. It's alarmingly simple, what I'm describing here, but actually, as I said, it's hard to solve for the very reason that this advection of vorticity is hiding the fact that it's a nonlinear equation fundamentally. So we're going to consider a simple case where the flow is inviscid, it's two-dimensional, it's on a bounded surface, here a sphere. The sphere will take the radius 1. It doesn't really matter what the radius of the sphere is, but it's easiest to take 1. The vorticity field, which is a scalar here in two-dimensional flows, or pseudo-scalar, the vorticity points outward from the spherical surface in upward direction and satisfies material conservation. So this capital D by dt is simply transport following Lagrangian particles, if you like, so particle transport. The flow is incompressible, so this expresses that R is a unit vector here drawn from the center of the sphere. So this is basically the normal vector to the surface. So it's tangent to the surface, and psi is a so-called string function. And if you put this in, then you can derive, I've skipped a lot of the steps, but out comes the so-called Laplace-Beltrami operator, which is just Laplacian on a spherical surface. But if you have other kinds of surfaces, this operator can change. It depends on the geometry of the surfaces. And the problem is significantly more complicated when you have deformations from a spherical surface. Again, I'm happy to talk about that later if anybody's interested in how things change. There's a mathematical requirement on all closed surfaces that the so-called Gauss condition, that the vorticity integrated over the domain, this is, area integral is equal to 0. So you can, and this is just basically Stokes' theorem plugged in here, and there's no boundary on the sphere, and therefore it has to be the case that omega is equal to the average vorticity is 0. So if you like, the total circulation is 0. Moreover, as I've alluded to before, that the invisible flow constitutes that this has many conserved quantities. It's an infinite order Hamiltonian system, in fact, with the Hamiltonian actually equal to the kinetic energy. So kinetic energy can be written as this way, and it can also be written by an integration by parts as the product of vorticity times string function integrated over the domain. This is a well-known result. And moreover, there's the angular momentum, or equivalently the angular impulse by an integration by parts, again, can be written as the vorticity multiplied by this radial unit vector. So it's a vector quantity, and this quantity is also conserved. Now, here in the results to be presented, we take the simplest case where the total angular momentum is 0. If you have non-zero angular momentum, it's actually very interesting, but leads to different final states. And this has been studied by a number of other people. I probably should give a list of references on this, but there's been other people who have studied on non-zero momentum, including Wan Ming in her thesis. So there's some results out there for that. It's a less interesting problem when you have finite angular momentum, because what typically happens is that the angular momentum basically gives you a polar axis, and the flow likes to rotate about that axis. Okay, so you end up typically with a large polar vortex at the northern hemisphere, or if you call the north being the direction of the angular momentum, and then another one at the southern hemisphere with the opposite sign, and that's your final state, something like that. When you have zero angular momentum, you can't get to a state like that. You can't have a northern polar vortex and a southern polar vortex of opposite vorticity, because that has a finite amount of angular momentum. So something else has to emerge in that case. Right, besides that, we have the material conservation of vorticity implies an infinite number of additional constraints, namely that any power of omega integrated with the domain is a constant. In fact, it's more than this. Any function of vorticity integrated with the domain is actually conserved. Now, this is just basically a countable way of counting the Casimirs, if you like, but in fact, any function of vorticity is. Another way of putting it is that if you imagine using level sets, so if you had, and this is the method that I'll be talking about numerically uses, if you imagine that you have piecewise uniform vorticity, this statement of conservation of the Casimirs is equivalent to saying that the area between iso levels of vorticity remains constant for all time. So now if you take the limit where you have an infinite number of iso levels to approach a continuous distribution of vorticity, then you have this infinite number of conserved quantities. So this could be thought of as equivalent to saying the area between adjacent iso levels of vorticity are conserved. It's another thing, it's also a statement of something called vorticity measure, borrowing a term in pure mathematics about the probability of finding vorticity on a surface. And we're discussing the vorticity measure in this talk later on. So it's the measure, the probability of finding vorticity of a given value on the surface is also a conserved quantity here. So there's a variety of ways of thinking about the Casimirs. The second one, the second Casimir is a special one that people often use, which is called entropy, because it's a quadratically nonlinear quantity, and that is used to, in phenomenological theories, which I'll come to in a moment, describe the so-called dual cascade of turbulence. This is it here. So the conservation, I think I've already mentioned this now. So the conservation of all the Casimirs basically means that the fractional area occupied by vorticity, this quantity here, is conserved. So P of omega will be this probability measure of finding vorticity of a given value on the surface. Now, we've known since Fjortoft 1953, at least theoretically, he suggested, has been followed up by Creighton and Batchelor, there's a whole long history of this, that there's a dual cascade that's typical of two-dimensional flows. So if you think about a random state, typically what people do is they say you have some initial flow which is of sufficiently small scale. Typically, it's a spectrally narrow banded distribution. I'll talk about that in a little bit. You basically so you think about K being like some kind of wave number, inverse wavelength here. What often people do is they distribute the initial conditions so that they're localized in wave number space, which means in physical space, it looks like there's disturbances everywhere and they all have similar scale. So it's like a pattern initial condition. And what Fjordhoff argued is that if you set this off, evolve this flow in time, then naturally the nonlinearity in the equations will cause the energy to spread to large scales, which is counterintuitive for people that think about 3D turbulence, which is where it's the opposite. Energy is cascading to small scales, and the entropy in 2 dimensions cascades to small scales. So on average, the mean centroid, if you like, the mean value of the energy or center is moving to the left, and the entropy moves to the right. There's some overlap here, so not all the entropy spreads to small scales. Some of it actually ends up at large scales. This is again a picture that you don't often hear talked about, but this entropy that's leaking to large scales here, you think about how can this happen, because you think of entropy being like filaments being shrunk. This is the Batchelor idea that as turbulence evolves, you create filaments, the filaments thin exponentially, and this is the entropy cascade that's taking place in physical space. But it turns out that some of the entropy is caught up in emerging coherent structures, like would dare to say Lagrangian coherent structures. They're different from the Lagrangian coherent structures talked about yesterday. These are actual vortices that can be identified as coherent regions which are preserving the particles that they're containing for long periods of time, maybe indefinitely. So there are coherent structures that are emerging in the flow, which are largely responsible for this energy cascade to large scales. And some of these coherent structures, of course, all the coherent structures carry vorticity. Inside that vorticity, there's entropy, which is just the square of the vorticity integrated over the region. So some of the entropy is actually trapped up in the vortices that are then merging and developing to larger and larger scales. And so that's why there's a leak of entropy to large scales. And so similarly, energy is not all going to large scales. Some of it's leaking to small scales. And how does that happen? Again, if you think about some vortex interaction taking place, like in the first slide that I had here, you form all these filaments. Well, the filaments aren't entirely benign. They're not passive material. They actually carry a little bit of vorticity, and therefore they carry a little bit of energy. Not much, but they carry some energy. And so some of the energy is also taken to small scales. And, you know, as an aside, people for a long time, especially in the weather forecasting business, were interested in trying to at least conserve energy and sometimes conserve entropy in numerical methods. So there's a famous scheme by Arakawa. There have been some other work, a whole series of papers afterwards, especially in the 80s, where they developed finite difference schemes or other methods that tried to directly conserve energy and entropy. And a picture like this tells you that you should do neither. Seems radical to do that. So I would argue that if you develop a numerical method which conserves everything, the numerical method is probably wrong. Okay. And that some people, I remember giving a talk at European Center for Reading Range Weather Forecasting. I can't remember the guy who was the director at the time, but he was arguing against me, saying that you can't say that. And I said, well, I mean, I was just pointing out this argument that you're going to lose some energy. You can't possibly keep it. And the problem is that any numerical method has a truncation wave number. Eventually, this energy distribution will move beyond the wave number and you lose energy. So you have to lose something. It may be small, but you might lose a few percent in the calculation. So that's the picture. So the classical phenomenology is that picture. Okay, so, and you know, we're all familiar with the fact that flows can get very complicated. And so the main thing that is doing this is the nonlinearity. So rewriting the vorticity evolution equation is this u dot grad omega, because u depends on omega. It's a quadratically nonlinear term here, this is what's responsible for the cascading that's taking place. That's all the nonlinearity in the 2D Euler equations is in this term and nowhere else. Everything else is linear. And so if you start from a broad scale initial condition or a moderate scale initial condition, then rapidly the vortices, or you see vortices starting to emerge and filaments forming, and it gets progressively more complex. You start seeing all kinds of small scale structures. So this is not just dirt, it's actually vortices that are developing in the flow here. You can get much more complex results than this. But this is a typical way that two-dimensional turbulence evolves. And I'm interested in basically what happens if you go much longer than this and not in a double periodic geometry like this, but on a sphere. All right, okay, so what happens as time goes to infinity? So the long-term fate can only be theorized, and I'll talk about some of those theories here. So this has been a popular area to look at what can possibly take place. The idea of simulations is thought to be basically impossible. You can say you can't at least conserve everything and go for t going to infinity using direct numerical simulation. So all laboratory experiments and numerical simulations, necessarily with dissipation, invariably produce a steady flow filling the entire domain. So up until I was at KITP in 2014, talking to them about this, the results up to then were about forming essentially a quadrupolar structure in this situation. So in the case that we're going to be looking at with zero angular momentum, you form a quadrupole. Earliest work that I know of is by Polvani, probably in the early 80s, mid 80s, where they were looking at flows on spheres. Polvani's been interested in looking at the gas giants and jet formation, et cetera. It's a different problem, but he also studied in his thesis this idea of the emergent state of flow on a sphere. But basically, numerical dissipation, you can imagine if you have a numerical method that has any dissipation, then inevitably it seems that dissipation will pull things down and grind them down to a halt. Something will happen, either the flow will dissipate completely, or it will become steady, and then be non-dissipative once it gets to a steady state. And this is what people have been finding. And there's a lot of theory then that was developing shortly after that time by Miller and Joven and Soberia, proposing theories for this final state in the flow. There's some important work by Bruce Turkington too, for people that are interested in following the literature further, that have gone further than this. But basically, they argue that the final steady state obtained in the aftermath of intense turbulent mixing is likely to be a statistical mechanical equilibrium dependent only on the inviscid constants of motion. So they're arguing that given the Casimirs, all the quantities that we know, energy, angular momentum, they can predict a final state that emerges from that flow. But since then, they've backed off from that a bit, and they said, well, evolve the flow for a bit, we'll readjust the conserved quantities, and then we make a prediction. It's basically difficult because inevitably any numerics or any experiment is going to be doing some dissipation, so you actually can't conserve these quantities. So there have been fixes for this theory to try to take into account some weak dissipation, and especially people like Bruce Turkington would, his work would take that a bit further. But in any case, these flows end up in a final state, which is steady. So this coarse graining theory is basically predicated on the idea that if you take a domain, each of these boxes, say of side length A, so each square here is A by A, you're going to basically average what's taking place. So there's complex dynamics happening in every one of these little pixels here, which goes on and on and on endlessly. And they're going to do some coarse graining of this and try to predict the coarse grain distribution. Of course, it's impossible to expect that any flow like this, which is cascading, even if it's getting smaller and smaller and smaller scales, it'll never become steady. It'll never become steady at all scales. But if you instead say that I like a computer screen where I can know this is my pixel size, it can appear to become steady, whereas in fact there's stuff going on below the scale you can see. And so that's this idea of coarse grain. And so they developed basically this idea that instead, you can represent the vorticity as the local probability distribution of vorticity in a region. So it depends on both space and the vorticity level sigma. You can have many different levels of vorticities. They sometimes took piecewise constant or a finite number of them or a continuous range. And they basically say that the coarse-grained vorticity that you observe is dependent on some distribution which they're going to try to predict integrated over vorticity levels. And so basically then in this theory, the correlation between fine-grained fields in different cells are neglected. So what's happening here is independent of what's happening here at the small scale, at the subgrid scale.
David,
Yes.
what do they mean by, what do you mean by steady? I mean the probability distribution.
Yes, so everything, this quantity here becomes steady.
Independent of time.
As independent of time, as you go to, so the idea is that you have to take this picture further and further and further and further in time. You can imagine all these filaments get thinner and thinner and thinner, getting closer and closer and closer. You could sort of imagine maybe this could happen. When is this mixing ever going to stop? You think that, well, if you have infinite time is a very long time, and it's unimaginably long. In fact, I was just thinking, I'm reading a book on archaeology of Britain, actually, and just the ideas of thinking back, 1,000 years, then 10,000, 100,000 years. You just keep increasing over time. It's unimaginable. So when you start thinking like a mathematician about infinite time, there's no such thing as infinite time. You take the limit as time goes to infinity, you have endless time to do something. You could imagine that if you waited long enough, maybe they're right. It could actually become steady. Okay. So what I'm going to try to show here is, yes. So sigma is basically the vorticity so sigma are the levels of vorticity. So you can imagine a distribution of vorticity levels. So they typically took 1 or 2 or 3 values in their flows, but you could actually write the theory for a general distribution of sigma. So typically, if you think of this as a sum instead of an integral over the sigmas, then you think of it as that I could specify like one value that's positive, one value that's negative. That was the simplest theory that was first developed. And then you can imagine having several, and then you can take the limit of more and more of them. Okay, it just gets more complicated when you write the general form this way. But that was the most exotic theory was for the distribution like this. But they all give similar results. Yes.
In practice, you cannot go to T infinity. So at some point you have to stop the computation. And what's the idea? It's when you pulse width, when you pulse in different T, basically you get a rule which is independent of your pulse grid.
All right, so the scale A here, of course, is itself in some way going to 0 as time is going to infinity, but the limits have to be taken carefully. So you need to take T going to infinity before A goes to 0 in that limit. So if you fix this coarse-grained scale A at some finite but small value, and you take T sufficiently large, it becomes increasingly steady until it becomes in the limit steady as T goes to infinity. But A stays fixed and finite. And then you can take A even smaller, you have to go even longer. It takes longer before things are starting to appear steady, but it's really never steady until T goes to infinity. Again, it's this concept of infinite time. It's really hard to understand. So they determine the equilibrium. I'm skipping a lot of details because I don't really understand Shannon information that well myself, but basically they're maximizing this entropy in the flow and trying to determine the final equilibrium by the so-called least bias local probability distribution, this rho of R and sigma, that's consistent with the fine grain flow being a 2D inviscid flow, conserving all the constants of motion. So they're maximizing this while conserving with Lagrange multipliers all the conserved quantities like energy, angular momentum, and the Casimirs up to infinite number. Okay. Well, as I've already mentioned now extensively, no numerical simulation can be carried out to infinite time, and we can only approximate the inviscid fluid behavior for finite time. And so you might argue that there's no way in this talk I'm ever going to get to the final result because I can't run the calculations to infinite time. But there are good reasons that emerge from the simulations that suggest that things will never become steady and this theory can't be correct. Okay. And the key thing is the flows in viscid. I'm not arguing this is true for a viscous flow. If you have a viscous flow or some kind of dissipative flow with the right kind of dissipation, the flow could become steady and finite after infinite time, but with no dissipation at all. If it's truly Euler equations, I don't believe that in general. I think I would call it a measure zero probability. So almost never will the flow become steady in finite time. So you may basically have to start with a steady flow to have a steady flow at the infinite time. So I think any other simulation or any other flow would stay intrinsically unsteady. So we took two very different numerical methods. And the main thing that really clinches it is a simplified model at the end to try to understand what's taking place in these results. To show that the central plane of MRS theory, coarse graining theory, the steady final state is likely to be false. Okay, so the unsteadiness that we see seems to appear for all time. So the first method that Wan Ming He and Brad Marston were using is the so-called geodesic grid method. I think Brad still has a little app that you can download from Apple if you're interested in using this method. It's based on a paper by Hikes and Randall in 95. And they basically try to use a quasi-isotropic grid. You can't have an isotropic grid on a sphere, but you can make one that's almost equal size cells. And there are D cells on them. It employs a so-called quad harmonic hyperviscosity of some exotic form here. So you can see it's a 6 orders. It's a typical hyperviscosity. Then it's got this 2 here and elsewhere. The 2 here is required to conserve your angular momentum. If you don't put the 2 there, then angular momentum will not be conserved. So the form of the hyperdiffusion or diffusion operator on a sphere is different from what you see in doubly periodic geometry, and that conserves the angular momentum for you. They employs fairly high order hyperdiffusion to remove entropy cascading to unresolved scales. And the second numerical method is so-called combined Lagrangian advection method, CLAM, that we developed in 2010. And this is in JCP, Journal of Computational Physics. It's a hybrid method. It's originally based on this idea of contradynamics. People know about contradynamics originally from the Burke and Roberts 65 paper, famous paper in plasma physics called the water bag model, where it came from originally, but mainly developed by Zybusky and other co-workers in the late 70s. Zybusky, Hughes, and Roberts is the main paper in the fluid dynamics or Euler equation literature. And they basically represented in 2-dimensional Euler flows. They said, let's suppose the flow had piecewise uniform vorticity. So in this case, I'm showing you 4 different values. There's, let's say, a 0 value outside, and then 3 different values. Some people call this level set methods. It's just a new name that's been developed to supplant, if you like, these contour methods. But it's a contour method here. The reason why it's called contour dynamics is that only the edges here, where there's a discontinuity in vorticity, need to be evolved in the numerical method. Okay, that's not quite true for what I'm doing here, but in the original contour dynamics method, which you can do in a spherical geometry, all you have to do is track the interfaces or contours that separate different uniform regions of vorticity. And the simple reason for that is that the material conservation of vorticity is exact. I can take any particle here, which is green, and replace it by one that's over here, just exchange them, and it doesn't change the equations at all. Nothing is, there's no effect on the dynamics by replacing 2 particles, the so-called particle exchange symmetry. That's the underlying material conservation of vorticity. As a result of this conservation, the only thing that matters is the separation between the 2 different levels of vorticity. So this is what became then the contour dynamics method. So the hybrid method basically uses material vorticity contours, these contours separating these different colors here, to accurately solve this equation. But also, alongside this contour method, I run in parallel a spectral method. So I'm using a spectral method, using pseudospectral method on a sphere to invert the a Poisson equation to find the vorticity on a regular latitude longitude grid of dimensions ng by 2ng. So I'm not going to, I can look at, we can discuss this later on if anybody's interested in numerical methods, but essentially in contour dynamics, what you end up doing is that even in this method, every contour here, edge, has to be represented by a finite number of so-called nodes. And the nodes are are connected by cubic splines to represent the curve. And the number of nodes can increase in time as the flow becomes more complex. And if you did straight contour dynamics, then the interactions require an order n squared effort to do the computation. So it gets expensive when the flow gets complex. Using an underlying grid here of some dimension allows you to circumvent the expensive part of contour dynamics, which is this so-called inversion to try to calculate the velocity or the motion of these contours. So find the velocity field can be then done on a regular grid, and like in a particle and cell method that's used for like points, can be interpolated, in this case by Bodleian interpolation, to the boundary points. So you give up a little bit on the exact inversion of the vorticity field to get the velocity field, but it's sufficiently accurate to find the flow down to small scales. So again, I'm not going to go, I mean, I could spend a whole talk or so on the method itself. Suffice it to say, small scales are eventually dissipated in this method. So I can't keep the filaments as they stretch to indefinite scales. So what I typically do is remove filaments that are thinner than 1/16 of the grid size, some average grid size on the sphere. And the magic number 1/16 came from many years of trial and error, trying to figure out what would be an optimal setting, but it's consistent with the smallest scale, which is still contributing significantly to the velocity field. Yes.
I missed the point on what kind of boundary conditions we use.
Right, the beautiful thing about the spheres, there are no boundaries, so no boundary conditions required. So if you think about
the sphere is bounded, so
oh yeah, so well, but it's a bounded boundaryless surface. So it is bounded, but has no boundary. There are apparent singularities at the poles. So when you do numerical methods like spectral method or whatever, you have to think about that. If you're using Legendre series, then the polar problem's gone. Because spherical harmonics automatically know about this. But using any other method, like we're using a regular latitude grid, in this case, actually it's called a half grid, so we avoid the poles, and you actually do the computations along great circles, so you actually you avoid the polar problem in this case. Anybody interested in literature behind these methods, I can give you details of that.
Just to kind of touch base with something familiar, at least to me, is there anything analogous to a Prandtl-Bachelor theorem for the sphere?
Mhm.
In other words, do you get homogenization with coarse graining or diffusion?
I think there
And then
isn't.
the question would be, does the song and dance with Lyndon Bell, which is what the MRS is really started from, does that, connect to that?
That's a good question. I haven't thought about Prandtl-Bachelor theorem in this context, but I can't imagine it's any different than on a planar 2D surface. So it should be there.
Exactly, but it gets to the issue of course, the boundary. I mean, the closed bounding streamline in the planar case is critical.
Yes.
But I was just,
No, that's a good question. Because the fact that you don't have a boundary on the sphere. That's a good point. Okay. So as I said, the effective resolutions were basically dissipating. We're doing so-called surgery, which removes small scale filaments at a fine scale. The effective resolution is about 16 ng by 32 ng in typical simulations. I'll be taking ng up to 1,000 or 2,000 in these calculations. So there's been some work, some by Steve Twice and myself here in 2012 that discusses this in comparison with direct comparisons with spectral methods to back up this. Yes. All right. So the point vortex method is relatively expensive compared to this, because you can't capture the really fine scale filaments efficiently using a point vortex method. Basically, the points have to fill the regions of vorticity. So you have to use, so he's talking about a general method that you can use to represent any series of any flow by a set of point vortices. And you can move these around. And this has been a popular method. In fact, you'll see the point vortex method later on in this talk, but not in the sense of describing the entire flow. But it's expensive to space fill a region here with enough point vortices that when the flow gets complicated and starts forming these filaments here, that you really can resolve the smooth extending filament. What typically happens with point vortices is that they clump and you start getting this false instability, like a cage instability forming, Kelvin-Helmholtz instability, which is the fact that you run out of resolution. Whereas the filaments that form in the contour method remain smooth as they extend. Okay, they can roll up, but the ropes are more natural in that case, the shear instability. So point vortex methods are relatively expensive. Having said that, I think they're the way to go in 3D. So that's again a different talk, which I'm not going to talk about this time, but we're doing some work on in 3D flows, looking at the evolution of clouds and convection, where we're using not points, but actually ellipsoidal parcels to represent flows in that case. And they can be very effective in that case. But in this context, the contour method appears to be about the most efficient method you can use for this kind of problem. And you'll see from the results that it's pretty hard to beat the method. These are calculations that are typically done on like a laptop, or I don't use supercomputers for this to reach the kind of resolutions that we do. I mean, we have with Steve Tobias, in our GFM paper, we talked about the fact that we were running a simulation trying to compare these methods. The highest resolution simulation that we could do in the MHD context was like 1,000 or 2,000 squared. Maybe it was 8,000 squared. 8,000 squared was taking like hundreds of processors, big parallel computer, many hours. And the comparable calculation in the contour method was a few tens of minutes or a few minutes in the calculation. So it's just completely different range or a different level of computation. And yet the results could be compared like with like. All right, so just to set the problem, all the simulations start from the same vorticity field. In fact, we only do essentially one simulation starting with exactly the same spatial pattern, but at different resolutions. So we take a set of spherical harmonics, which are in the paper we published. We get the exact coefficients are given, which looks like this. So this is like the North Pole. This is the South Pole. Looks basically similar, both sides. Typical vorticity values are order 2 pi, or roughly 5, 6 in that value. And it corresponds to an eddy turnaround time of around 2 units of time in this case. Root mean square vorticity 1.7. So nothing very interesting here. That's the initial flow, and it never stays like that. This is what happens at early time. So at time 4, so this is only two eddy turnaround times later, you start getting the characteristic wind up of the pattern. So this is showing that the different resolutions with different models are converging on the same solution. So at early times, the results agree. If you want to talk about hyperdiffusion, look here. You see these ribbons here? You don't see it in the so-called plan model. So all this is spurious hyperviscosity. And it's especially problematic around the polar regions. You see it prominently here. And this is after we've been careful to reduce or increase the hyperdiffusion coefficient enough to try to minimize its effect. It turns out you can never remove this overshoot undershoot problem. And this is especially problematic for simulations of weather and climate, where certain things like water vapor concentration shouldn't go negative, but if you use hyperviscosity, it can go negative. And so you have to then do limiters, which are diffusive in order to stop this from happening. So hyperdiffusion here is relatively benign, but not totally benign, but it can be more serious for other applications. So at early times, basically all the simulation methods agree. At later times, differences start appearing. So this is now 10 times longer at time 40. again, qualitatively, similar kind of flow with similar structures. This is using this, so the CLAM model here is only using 128 grid points on the basic grid and 256 in this direction. And you can get that kind of detail in the image. Of course, the image is being produced on a much finer grid because I have access to contours down to scales that are 16 times smaller than the grid space. And then if I go to 256, you can see that there's no, at this point, there's no convergence of the simulations anymore. And that's because we've understood from many years of experience that once you reach the point of, or once you pass the point of peak entropy dissipation in a flow, it seems that's the limit of predictability. So we're basically in a chaotic regime now where the flows are diverging. Even if you take slightly different initial conditions for the same resolution, the flows will diverge enough where they would be this incomparable at that time. So this is time 40. This is still early time. But you can already imagine, you can start seeing there are several main structures that are developing. There's one here, there's one here, one here, one here. There's your quadrupole. Yes?
Are you measuring entropy?
I'm not measuring entropy directly, no. That's a nice, that's a good point. It should be, we could calculate entropy in this flow, but we haven't done that. But entropy would probably be growing. Be interesting to know how rapidly it's growing in this calculation and how different methods are doing it. So now, if we look at the highest resolutions with CLAM 512 and 1024, you can start seeing it. Well, we're starting to get some degree of convergence. At least the large scales are converging. The small scales I wouldn't, but you know, even the structure here with a little tail of a filament there and there is converging. That structure there is roughly in the same place. If you go to a high enough resolution, you can get convergence for longer. Okay, but you only buy yourself a few units at a time. Very rapidly thereafter, you'll need to keep extending the resolutions to get convergence. By this time, the entropy, which is only the quadratic quantity in the quadratically conserved quantity, has decayed by a huge amount in these calculations, by 56% all the way to 32.4% at the different resolutions. So up to 1024, I'm still losing a third of the entropy at this point. So I can't conserve entropy, okay? Even though I'm using a really elaborate contour method to do that. My argument is that you can't conserve entropy. If you had somehow written a scheme, and I know there's a paper which I just reviewed for JFM, which I wasn't happy about, but there'll be something out in the last issue or so where people argue that there's a scheme by Seitlin where you can basically rewrite the equations and conserve all the Casimirs. Essentially what they're doing is they're folding this 33%, which is cascaded below the grid scale, back into the dynamics. And I feel like that's just aliasing. Okay, so you're going to get different results when you do that. If you have good eyes, I don't anymore, but if you look, you can see that there's a plethora of small scale structures. So on top of these big ones, you look at all scales, there are vortices developing of different sizes. Okay, and that's seen here in the vorticity power spectra. So it's a measure of looking at entropy again. It's a typical thing that people look at. Time 440, lots of different simulation results are superposed, showing basically you get an algebraic decay of the entropy, typically like k to the -1 in this case, for wave number to the -1, total wave number to -1 in this flow. So it conforms to the sort of classical theory of the entropy spectrum. You can see the different resolutions are here with the GGM method here, and then the highest resolution CLAM method out here. So now if you go to much later time, this is time 400, then 4,000. So I'm going up by factors of 10 in times. So by 400, now it looks like things have completely changed. All the small scale structure seems to be gone. It's not gone. You actually look carefully, these specks aren't just imperfections of the image, they're there in the flow. And there are fewer of them here. There's still some, but they're at smaller scales. Some of them are still running around there. So I don't think I have a zoom of one of these images, but if you actually look at one of these structures here and look closely, you'll see little specks like this rotating around it of the opposite color. Okay, so they never the small scale structures don't ever really disappear. They just get trapped around the main structures. So in the various methods here, you can see that this last time, both simulation methods are giving the same qualitative picture. You can see that here there's relatively little evolution from this state to this state. Here there's a bit more, but there's not much. There's not some unsteadiness that's taking place. Okay, so really the next question is, how steady is this? So this is showing the power spectrum of vorticity at later times, again forming an algebraic tail here. This is the k to the -1 spectrum. This part of the spectrum, by the way, is the filamentary cascade that Batchelor was forming his theory about dissipation of entropy in two-dimensional turbulence. This is the filaments cascading the small scales. This steeper spectrum here corresponds to the vortices that are forming. So we have this break in spectrum. We studied this in the paper in 2008 in GFM, where we talked about the emergence of a vortex population. There's not much of a population here. We have mainly 4 vortices. So, but yet nonetheless, the steeper spectrum has to do with the fact that you have now coherent vortices at moderate scale in the flow. So I promised looking at the vorticity measure. So this is the probability of finding vorticity at a given value in the flow at different times. So the initial state here is this black curve here, the one that's the broadest. So that's how we started the flow. So this is given a value of vorticity, say 2, this gives you the probability of finding that, or probability density of finding that vorticity in the domain. After a short time, so at different times, these are, in fact, I don't indicate the times here, but the latest times are these 2 times here, showing that the distribution becomes very peaked around vorticity 0. So that means the small scale vorticity has been preferentially removed, leaving mainly vorticity trapped in the larger scales. And this is what happens in CLAM. You might notice there's a difference here and here between the methods. And this is because in CLAM, there are no overshoots and undershoots. All that you're seeing here are high values of vorticity growing, extreme values due to hyperviscosity. And you don't have any increase in the maximum vorticity in the CLAM model. But the main thing is that this distribution changes and you get basically relatively flat regions of high vorticity with a broad region where you've wiped out vorticity. Yes.
The final state depending on the initial condition.
Yes, it does. All right, so we only looked at one calculation. We've also checked other calculations. What you get the final stage does depend on which initial conditions you take. And we don't have a general theory for that. But the degree of steadiness also appears to depend on initial conditions. This is studied more extensively in Wan Ming's thesis, where she looked at this, and I'll come to this in just a moment. Another measure people often talk about with steadiness is to basically make a scatter plot of vorticity versus stream function. If you had a single curve here, which was infinitesimally thin, it would say that you're in a steady flow. Vorticity is functionally related to stream function. In fact, we have, it's more complicated than that. The 4 extremes here are the 4 vortices that are forming in the flow. So here they are here. If you look at the CLAM results, you might see what looks like, again, pieces here, dirt, if you like. These are small scale vortices that are inside the flow still that haven't been dissipated. There's a whole series of small vortices that are contributing here. And also the fact that the curves are spread indicate that there's some degree of unsteadiness still left over. Okay. Of course, we're at time 4000, it's far away from infinity, so we can't really say much about that. So what Key and Marston then developed was, and this is in her thesis, and then in a paper afterwards, they developed a way of measuring the unsteadiness through an amplitude rotational invariant measure, W. I'm not going to explain how this develops. I don't understand it myself, but they basically express the vorticity of a series of spherical harmonics, and you look at the first few harmonics having to do with the second level, L equals 2, you can form a quantity here, which is easy to calculate in a spectral method. And so I did this also in the in the contradynamics method as well, or the CLAM method. So we calculate this quantity in both simulations. The quantity ranges from -2 to +2. And they said that when W is equal to 2, there are just 2 vortices, while when W equals 0, there are 4. So they can basically indicate from the sign of W, they can see which is the dominant pair of vortices. So Wang-Min-Key and Marston looked at angular momentum not equal to 0, as well as angular momentum equal to 0 and other initial conditions. So this paper here would describe the more sort of wider variety of flows. This is just to show you. So in their method, the GGM method at the highest resolution, out to 10,000 now, this is basically what the measure looks like. So at early-ish times, you see, and this is a zoom here, you see there's an oscillation taking place. Maybe not that substantial, perhaps, but there is an oscillation. The oscillation doesn't appear to decay out to very long times. And at late times here, you have this persistent oscillation taking place in this measure. If you do the same thing in the CLAM method, during the same periods, you see again the same kind of oscillations taking place. The range of values is slightly different, but you have the same oscillation with apparently the same period. So then we calculated that period. So you basically take the whole range. So we took basically the frequency spectrum. This is just a small sample of it. We took the spectrum over a much longer period from the very beginning, but over just a small section of it, here's the oscillation take place. You can see there should be a period, and the period is about 19. And so if we do a frequency spectrum of the signal, then we get this dominant peak. This is in log scales, log base 10 scales. This is huge compared to everything else here. And these are secondary echoes of that main peak there. So we have a main peak is 19.14. And the 19.14 corresponds to the motion of these vortices. The vortices are oscillating in some kind of state, dancing around each other at this type of period. So we observe 4 main vortices. They're all jiggling around at this oscillating around. So we thought, okay, to try to really understand what's taking place, maybe what's happening is that there are 4 vortices that are effectively no longer interacting. And for that, to really understand what happens at much later times, it's much simpler to say, what if we take these 4 vortices represented by point vortices now? So we're going to basically concentrate the circulation of each of these structures into a single point at the centers of these. That's what we've done. And then we run a much simpler point vortex model. This is just a set of ODEs for point vortices in spherical geometry. You have to solve these equations. The gammas are the circulations, and you just sum over the vortex positions, excluding the self-interactions. So this is basically the entire dynamical system. It's again a Hamiltonian system for point vortex dynamics on a sphere, and you just evolve a much simpler set of ODs, which is very quick. So what we did is we took the vortex centers and circulations, extracted them from these results at time 4,000 using a vortex identification tool, some sort. I'm not going to go into details. They were adjusted so that the angular momentum was 0 to be consistent. So we basically had to displace the vortices slightly. So the vortices were then, or the circulations were adjusted by around 10 to 15% to ensure that the angular momentum is 0. So this is what the distribution of vorticity looks like for the 4 vortices. It's got a steep section in the middle and then falls off rapidly with distance away from the center. So what we then did is we ran the point vortex model. It's nearly trivial to evolve. It's 10 to 10 times more efficient than CLAM. So we can run much longer. We ran this model out to on the order 10 to the 9 units of time, no change. So this is an oscillation that persists. So this is basically going back to the results for WT, this steadiness measure, we have this oscillation. For the point vortices, we got this smooth curve. So I've sampled the curve much more frequently than here. This way, the smooth appearance. The amplitude slightly reduced in terms of oscillations, but the period looks like it's about the same. Is it?
What initial condition?
All right, so the initial condition, as I said, we took the results at time 4,000 from the CLAM, and this is what the vorticity distribution looked like. We then basically took all the circulation inside these vortices and put them into a single point vortex at the center of these structures. That was our initial condition. So we started at time 4,000, then we ran forwards. Okay. And then we calculate the frequency spectrum. So the blue curve corresponds to the frequency spectrum for the point vortices. And the black curve is the previous result that we calculated for the CLAM simulations, the full Euler equations on the sphere. And the peak here matches very, very closely. So we also have a perfect match of the frequencies. So we have seen that basically the representation of these 4 vortices by 4 points matches very well the dynamics. So we believe that oscillations will never die out in point vortex models. It's an intrinsic property of the point vortices that they'll persist for long times. And this led to another work afterwards, which I'll briefly talk about. And then the motion, we think, is quasi-periodic indefinitely. So again, I'm not going to discuss any of these results here, but that led on to another paper where I was studying the equilibrium and stability of 4-point vortices on spheres. It's actually a pretty exotic problem, it turns out, because the results depend on angular momentum, which I, in this case, looked at non-zero angular momentum as well. But what this paper was about was just trying to find all the configurations that were steady or steadily rotating on a sphere of 4-point vortices. So we want to find configurations where the different distances between the vortices never change in time. And then some of these are unstable and they move around in exotic ways. So that paper was really discussing the stability, when you have stability, when you have steady behavior. But there's extensive regions of unstable behavior for 4-point vortices on a sphere. Remarkably, these are all configurations for 4 equal vortices. So they all have the same circulation, all equal to 1. So this is non-zero angular momentum. But there are actually 7 configurations, some of which don't have much symmetry and are not easy to figure out by any kind of guess for the state. So some kind of random search method had to be used here to work these out. But that's another problem altogether. Yes.
You were saying at first that you had this data of big eddies, and you had combining smaller ones.
Yes.
Since you're looking at team, you're saying that basically all of the small ones.
No, so in the full Euler equations, those small vortices will probably persist and they'll remain as in the GFM paper, we show a zoom of, I should show that here, but if you look at any given vortex at the final time in the CLAM simulation, you'll see these little specks of vortices that are of the opposite sign that are embedded in the flow. They're kind of like planets stuck in, a circulating flow. And because they have opposite sign to the main vortex, they are particularly stable. So they're held there without being sheared away. So they can, I think, persist indefinitely. So the picture I have is that you have the main vortices, but inside each main vortex is a whole spray of small scale opposite sign vortices that are moving around in a circulating in that flow, and they never die out. But that's what in the psi omega relationship, which I showed, all that little spraying that I saw in the CLAM, the up and down vertical lines, were due to those small scale vortices that were trapped. Yeah. But I mean, a simple point vortex model couldn't represent that too. So this is the simplest thing we could do. All right, I don't know what time I am. I probably already.
Well, it's 10 past 10, but you've got plenty of discussion, so carry on.
You sure? You want me to carry on? Okay,
Yeah,
all right.
yeah.
The next part, I promise, is shorter, so I can probably
I'll-
finish
I'll
this in
shut
10
you
minutes.
up when you get
Yeah,
to
you-
that.
I was worried I didn't have enough information.
Okay.
Okay, this always happens, sorry. So now for something completely different, as Monty Python would say. So not quite completely different. So we're now going to look at the so-called quantistrophic model. And again, yes.
Have you tried, when you study for what is it? Have you tried studying just for example 2 and see if have you measured properly the interaction, the binary interaction of the
All right, for 2 vortices on a sphere, they're always steady. So any 2 vortices, If they're of different circulation, will rotate about some point on the sphere. If there are opposite vorticity, that's the special case where they move around like this. Okay, but otherwise 2-point vortices are boring. 3-point vortices become interesting, but they're not that interesting because they're integrable on the sphere. 4-point vortices on the sphere, it's the first number where it can be chaotic. And in this paper here, I talk about the evidence for chaos in the system, which has never been studied extensively. But I mean, just one last thing about this is that if you take all different circulations, just random circulation values, then you try to say, how many equilibria can I find for 4-point vortices? There are cases where the number of equilibria that you can find, different ones that are distinct, come to almost 100. You can't imagine there could be 100 different initial states. Exactly what that number is controlled by, I have no idea. I've also looked at 3, 5, 7, 6 and 7 vortices, and the number of equilibria explode with the number of vortices that you have. Okay, so there's many different equilibria. It's a complicated problem. Yeah. All right, so the next problem I'd like to talk about is back to a doubly periodic domain here, and I'm just going to look at the so-called quasitrophic model, which I'll talk about more later on today for those who are interested where it comes from. The similarity with Euler is that you have a materially conserved quantity. Now I call it Q rather than omega. It's called the potential vorticity of geophysical fluid dynamics, or PV for short. The flow is still 2D incompressible. So in the planar geometry considered, it's just you can use a stream function. You can represent the horizontal velocity field, the full velocity field in this way. Now the only difference is that the relationship between stream function vorticity is now this generalized Poisson problem, which has this inverse, or this KD, which is the inverse LV, the inverse Rossby deformation length, or sometimes called the Rossby deformation wave number, more appropriately, since it looks like a wave number if you were to use a spectral method here. So the only new feature really over the Euler model just discussed is this new parameter KD. Okay, and well, that's interesting. It's not right. There's some again some work on steady flows for this model unfolded by this parameter KD, and it turns out that the equilibria that we know in 2D Euler can be extended in more complex ways when you have non-zero KD. In fact, what we found, this is work with Taoufik Hamidi in Rennes, that you can take, so when KD goes to 0, you go back to the Euler equations, 2D Euler that I was discussing in the first part of the talk. So what we did in another paper is to look at equilibria of the system, which are steady or steady rotating, and we found that you could take KD finite, find equilibria, then take the limit of KD going to 0 and discover new equilibria that were never known for 2D Euler that way. So you go around the back door. You can't actually reach those 2D Euler equilibria by a deformation from simple shapes like a circle or an ellipse. But that's a different matter altogether. All right, so here we're going to talk about KD actually being large now, so the LV scale being small. This is the so-called shallow water model where it comes from. We're thinking about a rotating flow with a free surface, and how the KD depends on that is discussed later on today. Basically, the model has to do with a free surface flow like this. And the typical scale LD is the typical scale over which the height of the free surface varies. And stream function is proportional to the displacement of the free surface. So this is really work with Helen Burgess, which was published in a Rapids paper of GFM, and I'll bring you up to date with some new stuff we've done in the last few months on this. So we started with an initial condition like this. So this is our Q field here in doubly periodic domain on a 1000 by 1000 basic grid. In fact, we're using this CLAM method, so it's effective resolution 16 times finer. We take a distribution of this is wave number now. This is the distribution of entropy. C of k represents the entropy here, the PV or Q squared. So it's peaked at a wave number KD around 40. We're equal to the same thing as the peak here K is equal to the deformation length here for simplicity. A subsequent paper looked at how if we chose this distribution, either broader scale, larger scales or smaller scales, how the things would change. Beta has to do with the planetary vorticity gradient, which we're considering 0 here, but we've also looked at cases where beta is equal to or non-zero. So first of all, we ran this calculation to a ridiculously long time. So the calculation was actually running on a machine in St. Andrews for 2 years and 4 months. And we just let it go and let it go. And then finally, we started looking at the results after a couple of years, and they look pretty interesting. This is well into the calculation. This is still early time, 10,000, 400,000. So we're showing the energy spectrum. So again, log scales here. The bold black line here is the total energy, which has the beautiful power law shown here, which is close to in these two-dimensional flows closer to K-3. I put slopes here. I've broken this down into kinetic and potential parts as well. Kinetic energy is shallow at small scales, but broad, weaker at large scales, and potential energy is the reverse of this. And the two curves cross necessarily at the deformation wave number KD40 here. So the main thing here is that there's actually very little difference between these flows, except for these two times, except the peak here has moved to larger scales. So it's again, the progressive growth of scale. And this is what you see. This is it. Actually, the first time is 27,000 units of time. The eddy turnaround time, based on the dynamics here, is 1. So this is about 27,000 characteristic times. And then 125,000, 343,000 here. The actual simulation goes to even longer than this. So this is showing the potential vorticity field Q with negative regions blue and positive regions red here. At the early times, you see the growth in scale here and the growth further in scale here. It looks very different from the classical two-dimensional turbulence situation. Now, the deformation length here is a tiny fraction, probably the width of this red dot that's on the screen here, compared to the scale of these vortices. These vortices that are developing are huge compared to LD. And this was not expected. There's asymptotic models that people developed saying that, again, this flow would freeze. There'd be no further dynamics taking place. Whereas what we find is that the flow continues to evolve. There's nothing that seems to stop the flow from evolving. It's just slowing down in some self-similar way. The corresponding kinetic energy field is shown here and showing something very interesting, especially at the late time, you see these rings. So the rings correspond to jets of flows that are running along the edges. So every edge here corresponds to a jet and a stagnant flow inside and outside of it. And the width of these jets here is the scale LD here. So that's the typical jet scale. So they're narrow jets that are intense, carrying fluid moving around these jets, and occasionally these interact. So these brighter regions here correspond to interaction points, higher kinetic energy regions. Another feature here is that we see again with the PV measure now, like in the previous part of the talk, we looked at the area occupied by potential vorticity above a given threshold. And as time evolves, the last time 664,000, the computer was turned off for maintenance at that point. That's the only reason we stopped. At 664,000, you find this emerging staircase developing the flow. And so this is another talk I could give about staircase formation, but a typical evolution of these flows that are envisaged is that you form staircase distributions of potential vorticity. And at each of these jumps, there's the jets form on these sharp fronts. And this was originally argued by Michael McIntyre in '82 that the jets emerge from inhomogeneous mixing. And he was thinking then about the Earth's atmosphere, thinking about potential vorticity and how it's distributed with respect to the pole to the equator. He's saying that if you basically start with a relatively smooth distribution of potential vorticity, and then you mix it in some region, the pole to equator difference stays constant, but the mixing necessarily steepens or flattens the region of potential vorticity here, and necessarily then steepens potential vorticity here and here. This is what gives you the so-called polar jet, and this can lead to a subtropical jet in the atmosphere. So the mixing is understood. Okay, what we observed in this flow is that many quantities follow a t to the minus 1/3 decay. In fact, the number 1/3 appears in so many different results in both 2D barotropic, like I discussed in the first part of the talk, in a different context. We're looking at, in that case, looking at the evolution of a large number of vortices on a spherical surface and looking at their number, how they're changing in time, the entropy. We also found a similar 1/3 decay in that time. And the question is, why do these quantities decay? So here we're showing in the bold, here we're showing the entropy Q, so-called potential entropy, it's decaying. This is time in logarithmic units down here. Then various other quantities, there's a dotted line shows a t minus 1/3 decay. The dashed lines here correspond to a rescaled kinetic energy and a so-called another type of entropy measure, which isn't the appropriate one, is decaying more rapidly. Like I talked about Z here. And then we have other measures of like a typical vortex radius or size compared to the deformation length and showing how it's increasing. So these are also increasing like approximately t to the 1/3. So there's various fits here of this behavior. So the question is, why is this 1/3 developing? Okay, so we came up with the scaling argument. And the scaling argument is very simple. So we consider, for simplicity, suppose we have some number n, which may depend on time, does depend on time, vortices with a characteristic or typical radius r in the flow. And each one of these vortices, like in the images before, they support long frontal waves. So these are waves that exist. These are by no means circular structures. They consist of wavy boundaries, and the wavelength of the boundary, the wavelength that's on the boundaries is considered to be proportional to the vortex radius. There's no other length scale in the flow. We're arguing here on the basis of self-similarity that the scale LD is so small compared to everything else taking place now that there's nothing left in the flow that could decide the scale. So the only plausible thing is to say that the wavelength of the waves on these structures must be comparable to the vortex radius, because that's the only comparable length. The boundaries are what are called jets. Now, as the flow decays, it slows down, obviously. And we identify a characteristic frequency. Again, there's nothing in the equation that tells you a frequency scale. Well, there are actually other quantities. There's the potential vorticity, which can be thought of as a frequency, but that's a very short high frequency that corresponds to the flow around the fronts. Okay, and that's not what we're interested in here. We're actually interested in how the shapes of the structures are evolving in time. If I had a steady circular structure which had a rapid flow around the edge, it's steady. So that rapid flow has nothing to do with the steadiness of the distribution. But if I have waves on it, the waves then oscillate at some frequency. And so we're saying that the actual evolution is controlled by the oscillation of these waves. And so we said, okay, well, we identify the characteristic frequency by the inverse time. It's the only relevant frequency for the slowly propagating long waves. And then I already mentioned this, that we need to take the wavelengths of the boundary waves comparable to the vortex radius. And then we go back to earlier work where we're studying the linear dispersion relationship, or actually the nonlinear dynamics of long frontal waves in the system. We found that when we have long waves, when lambda here is large compared to LD, the frequencies are very small. They're scaling like inverse cube of the wavelength here. Okay, so this is a result from this paper. And so it immediately follows, if you take omega to be t to the minus 1 here and back out the calculation, taking LD or omega to be omega to be r here, you can follow that r then must decay like t to the minus 1/3. In fact, I think there's a type of t, r should be increasing like t to the 1/3, not minus 1/3.
About 5 minutes later.
All right, almost done. Okay, then further predictions are that the PV conservation tells you that the total area, number of vortices times their area, r squared, typical characteristic area, remains constant. And then from that, you can basically, since we already know what r does, we can work out that n must decay like t minus 2/3, and this is the scaling we observe in the dynamics. So this also fits well the predicted scaling. We can go further. We can even look at the total perimeter or jet length. The total perimeter is comparable to the mean radius of each vortex. There's n of them. So this should go like t to the minus 1/3. The kinetic energy, as we've seen, is distributed in bands or ribbons. It's concentrated on jets, and you can actually use the velocity of a straight jet to work out that the kinetic energy must scale like the arc length on the boundaries. And this is then decaying like t to the minus 1/3. And again, this explains the decay of t to the minus 1/3 found in the results before. Okay, so to summarize then, we looked at other results. So this is further work in 2022 where we looked at dependence on the initial relative, the initial flow scale compared to LD. And depending on the scale ratio, you get either more vortices or less of them at late times, but the same kind of decay, t to the minus 1/3 or t to the plus 1/3. So in conclusion then, unsteadiness persists, results from, in the first part of the talk, very different numerical methods at many different resolutions, as well as reduced point vortex model indicate the persistence of unsteady motion on an invisible flow on a sphere. And there's no equilibrium final state. At least we think that's the case. And this must be due to the fact that complete ergodic mixing is impossible. We think that these results undermine these kinds of theories, hypothesizing complete mixing in phase space, a flow visiting all possible configurations with the same constants of motion. In the second part of the talk, with no diffusive mechanism, tracer fields like vorticity in 2D and PV and QG develop staircase structures, a consequence of inhomogeneous mixing, and that self-similar evolution is common. In QG turbulence, the relative deformation length does not impede or is not a break for the growth in scale. This is only limited by the domain scale, and we didn't simulate up to the domain scale in this case. The evolution is self-similar and inherently unsteady. Front sharper between uniform PV regions, lengthen and constantly meander. Okay, so there's future work. I mentioned already, advertised that we've added a planetary vorticity gradient. That you get similar things. You get jets emerging in this quasistrophic system with now not only now the jets can actually propagate or extend across the domain. So some work on this. If you're interested in this in JFM, we've also then been looking at planetary flows in shallow water models, looking at the emergence of jets with topographic forcing. So with that, I will say the end. Sorry to overuse my privilege.
We do have time for some questions and discussions. Yeah.
The fact that unsteadiness persists, but complete absence of dissipation, does it mean it has some implication on the very low dissipation system?
Yeah, so I mean, as I mentioned, in both in astrophysics and geophysics, Reynolds numbers are so astronomically large that for realistic times of calculation, these results are relevant from that point of view. But the caveat as this is a very simple model. I mean, 2D Euler, no background rotation. You can't trust it for that point of view. But it's telling you something that one shouldn't be maybe throwing all your eggs into one basket and saying that we should expect a steady flow. This idea of mixing is taken too far sometimes. People think that mixing is such an efficient process. It's not that it's not that efficient. We already seen yesterday this, the idea of these barriers, transport barriers emerging. It's the same thing. The staircase is emerging here. It's been a common feature here. These barriers already are putting a brake on this kind of potential mixing from taking place in the system. So I think it's generic.
Two questions, somewhat that aren't really related. In the game of the constraint relaxation, is it at all useful to think in terms of probability fluxes? And in particular, I mean, that comes to mind again for bounded sort of two-dimensional systems. It's a natural way of looking at it. But you didn't, I noticed you didn't really talk about sort of transport probability in the sphere, but maybe because of just its isotropy and homogeneity. homogeneity, but has that been, any comments on that?
Well, it's part of the reason for doing the sphere was to exploit the isotropy of the surface. And I have to think about Prantor Bachelor now in this context.
Well, yeah, or even more generally,
Yeah.
the transport of what you call rho.
Yeah.
Right, and that becomes a natural for describing a lot of these things, for example, like mixing processes
Yeah.
and so forth.
I haven't really given enough thought to be able to answer that in a coherent way, but it could be that the homogeneity of the flow and the isotropic geometry makes it difficult to escape anything but, you know, the conclusion things will become steady. And you're going to get basically a circular patch somewhere developing. The zero angular momentum case is a bit weird on the sphere because you cannot get just two vortices developing. So it has to be that you get at least three, but typically you get four, and they can be of different unmatched circulations. That's what led me on to this 4-point vortex model as a way to explore more broadly the kinds of unsteadiness that persists there, thinking that what's ultimately happening for any Euler flow on the sphere is that it in the coarse grain sense, in some coarse grain sense, it's emerging into four distributed vortices that can be well approximated in terms of dynamical interactions by point vortices. It's not a perfect model, but as we've seen, it matches the frequencies that are being observed in the two systems. That's not really answering your questions. Again, I'm taking you away from somewhere else. But you have a second question, or?
Yeah, does your wedding cake staircase coarsen in time?
No.
That's interesting.
Yes.
And why not?
It doesn't, because there's no forcing mechanism to do that. If I added forcing to it, there's a possibility that the forcing could interact with the staircase and start smearing it up. But without forcing, it's an interesting problem that I've been thinking about so the simulations which I briefly showed here, a lot of these are forced. Okay, so we've actually forced the flow here to form these structures. But I've also done some simulations which I have not fully looked at. I believe that you can do this without forcing. That if the scale LD, this deformation like this, small enough, that the freely decaying flow will emerge into a pattern like this, which will persist then with very sharp gradients for long times. But the forcing itself is actually the only mechanism that's able to combat the sharpening of the point four of the potential vorticity fronts.
Xavier?
You mentioned the case of traces transport barriers, but what about the case of the speed when you have four vortices? That's stellar. There be mixing and so what would be the time scale? It's slow.
Well, the point is that, all right, so I'm not going to try to go back and show results, but we found that the four vortices that emerge develop a weak staircase structure to them themselves. So even in a system where one might not think, in fact, I remember when I talked to Michael McIntyre about that, he said, of course you should see that. Typical Michael McIntyre say, so he wasn't surprised at all that you see this. He just says that you have a vorticity gradient, you have some kind of turbulence, some kind of mixing, maybe wave breaking that will redistribute just like in his cartoon, and you form at least a possibly leaky transport barrier. But if you can continue mixing, then that barrier can sharpen and sharpen. Now, as Pat was saying, if you mix by throwing in forcing, then there's a competition. The forcing can actually weaken the gradients slightly around these sharpening fronts, so you don't get ever a perfect barrier. But there are seemingly limits of these equations where the LD scale, this deformation length, if it goes to zero and you do a free decaying case, you really can get a indefinitely sharp barrier. The 2D order case is a bit strange because it doesn't have this LD scale, yet it still shows at least weaker, I wouldn't call them barriers anymore, but you do get the staircase formation, but it's broader, more broadly distributed. So it's not quite answering your question. There is mixing taking place still in these flows, but the ultimate state of these four vortices that are then far enough separated that they no longer strongly interact seems to be a point where the mixing is effectively arrested. There's very little, except maybe at the very small scale, some small mixing is still taking place. There's clearly going to be some wave breaking and filamentation, but they're very, very small scales at that point. And the main vortices is just sort of jiggling around at that point and not mixing any further. GGM, yeah. At late times we don't, but at early times that's why we.
No, I'm sorry.
Yeah.
You said your plan is much cheaper,
Right.
than a big.
All right, so we can compare things like, there are various things you can do. At early times, of course, you can actually compare, you can do difference images of the vorticity. See how well do they agree and how rapidly are they converging? You can look at spectra too.
When you compare it against something with a finite balance.
Well, the GGM method does have effectively a finite Reynolds number, but it's not a typical Reynolds number because it's based on hyperdiffusion. But there is a dissipation taking place there. If I were to try to do this with an ordinary molecular viscosity, it'd be impossible. I mean, you'd have a very rapid decay of the flow from early times. You wouldn't be able to reach these kinds. You'd have to have ridiculous resolutions to prevent that decay. I'm not sure I'm answering your question.
No, sorry, I'm not asking you that. But you said you've done some simulations, I think, to 8,000 square,
Yes,
which would have a finite balance number,
right, yes,
and compare them to your plan method, which is much more efficient.
yes.
How do you know, in that case, how do you know what finite balance number?
Okay, in the work with Steve, I believe that the vorticity evolution in MHD was done with hyperdiffusion. And the tracer evolution of the magnetic potential was done with just the usual magnetic diffusion. And that was done in both methods the same way. So the nice thing about CLAM is that certain fields can be taken out and simulated if they're thought to be large scale or diffusion is important, like magnetic diffusion. You can keep them on a grid and never use a contour method for them. So in the comparison with the MHD flows, we're looking at in that case, except through diffusion. So all we can do really is compare a given resolution, the state of the art at 8,000 squared, what's the lowest you can, how accurate can you get? And then we can compare the CLAM results against that. I mean, it's really hard in this business. I mean, it's basically, you get your hands dirty a lot because people don't like the fact that you can't get the exact results. And the flows are only interesting once you reach a turbulent regime, but then you lose predictability. So it really gets hard to compare like with like at those stages.
Another question, and you'll find that in your QG.
Yeah.
The one you ran for 2 years.
Yeah.
What is determining that immensely long time scale?
It's the fact that, so as I said, the frequency is decaying like 1/t. So the flow is slowing down all the time. So at the latest time, the frequencies are so slow, but they're not zero. They're just decaying all the time. So you have to run those times because at the late evolutions, there's almost no motion that's taking place anymore on these PV fronts. You have to wait for a long time to see a slight evolution of the waves propagating, but they're still propagating. It's still moving. The interactions between these structures, they're drifting very, very slowly and they collide occasionally. So you have these rare interactions taking place. But it never stops. Yeah.
Sorry.
Do you have a feel of an optimum forcing to get a strong staircase? I'm asking because, for instance, in plasma, of course, and probably in many other systems, you have a distribution of forces. You have a large field one, you have about, for instance, we have fronts, avalanches, whatever, we can pitch on those steps. And so you have very different mechanisms. So
Yes.
you have a feel.
Yeah, so we've done a fairly extensive exploration of forcing types, from what's called topographic forcing to spectral to vorticity forcing. Not only we've done the forcing in both narrowband and broadband ways in spectral space. We've also put in physical forcing, where we've actually inserted little structures of vortices or dipoles or something in the flow. We've done all the different types of forcing. But generically, what we observe is that almost independent of forcing, we get the staircase formation. We get the same kinds of behaviors seem to appear for all the different forcing mechanisms. But it doesn't answer your question about what's the most efficient forcing that does this. I don't know that answer. That's a great question to ask. But I suspect it's the forcing that would be optimal would be one which would not interfere with the forming staircase, that would preserve the gradients that are developing. So you want a forcing that somehow knows about the gradients that are there and avoids trying to contaminate them. So that would be the perfect forcing to basically sharpen the gradients. I haven't done that though.
But you should think the other way around as well, and have, for instance, if you have a front which carries some vorticity to the right side of the left, and when it falls onto your step, so it's a very efficient way to
Yes, but typically, if you have a step at vorticity and you throw a forcing anomaly on it, it tends to broaden the step slightly in that region. It could cause a little bit of wave breaking take place. It also, there's some vorticity that now has been added onto what's there before, and it's going to have to be filamented away and mixed on either side. So it tends to try to break it down. We actually did this I remember doing a simulation where I was looking at a single step in vorticity in a domain, and I put a bunch of very weak point vortices around, which would they weren't added in, they were not forcing, they were just basically there as a very fine scale noise for all time. And I wanted to see how that would affect the distribution of this this PV front. But in fact, the front persisted for all time. So even though it would cause micro breaking, but the front would form back again. It would, even though it's being constantly attacked, there's some kind of, in other words, it reaches a balance with the forcing. So the forcing effectively is probably controlling the effective smearing of these fronts that are taking place. The weaker the forcing, the sharper the gradients. And that makes sense because as you take the forcing to zero, and if you have the right system, like you take the scale of the system to infinity, and the right limits, then you get the perfect staircase. You get a very sharp discontinuity developing. So I think that the forcing controls the distribution or the spread of the mixing across these fronts.
Okay, last person to torture, David.
I'm not tortured.
Do you ever observe any sort of like echo phenomena in this relaxation, like butterfly flexes wings? One of the reasons I asked this is because sort of one interesting thing that's been established recently is the sort of relationship between T goes from campaign. How much stuff with small scales. So suppress the layer of stuff that echoes forever. In this case,
No, that's a good point. I think the forcing, the idea of the initial conditions or forcing is an area that effectively comes with an infinite number of parameters to choose. And we couldn't possibly have looked at all of them so far. So the distribution of your initial conditions could well affect what ultimately takes place at late times. If you start with a distribution of, say, vorticity, which is unnatural, so in other words, has a spectrum which is even shallower than what's typical 2D turbulence, I think what will happen is that you will rapidly burn off the small scales by forming intense filaments. And it will just basically relax back to the K⁻⁻₁ spectrum at late times. And likewise, if you start with a distribution which is too steep, it will shallow, and shallows by the formation, by shedding filaments in unsteady flow. So there's, and that, at least for small scales, the small scales seem to want to relax to a typical Batchelor spectrum, a K⁻⁻₁ in 2D flows. Large scales are completely different. That's a system, that's an area which, surprisingly, all the energies in the large scales and almost no one looks there. Everyone looks at the tail, which is unimportant. But you know, it's like the dog, you're calling him. But yeah, so really interesting things are happening at the intermediate large scales. That's where you form vortices and all the entropy is actually being trapped in these structures. All the energetic motions are actually in these larger scales, and that distribution, at least for forced flows, is sensitive to the forcing, as far as we know. People have been arguing about K⁻² spectrum or K⁻⁵ spectrum. There's no consensus yet on that 2D flows. And this is only 2D.
Okay,
Thank you.
again.